Okay, and as we move forward, we're going to look at gas stoichiometry. And you remember that earlier on, when we dealt with stoichiometry in chapters 3 and 4, we said that we could never take a balanced equation and use that to convert from grams of one substance to grams of another substance directly. We always had to proceed through moles. And then we would use a balanced equation. We would always use a balanced equation to relate the moles of a reactant, let's say, to the moles of a product. Okay? Moles of a reactant or product can always be related to grams, but what's important is that you understand that we can't go from here, grams, to grams directly. That's impossible. Okay, so we want to keep that in mind when we look at gas stoichiometry problems like the following. The reaction of a copper penny with nitric acid results in the formation of a red-brown gas composed of nitrogen and oxygen. A 0.289 gram sample of this gas was collected at 0.957 atmospheres and 291 Kelvin in a volume of 157 milliliters. What's the molar mass of this gas? If we think about our ideal gas law, PV is equal to nRT. R is a constant. We have the pressure, we have the volume, and we have the temperature in Kelvin. What we can solve for is the number of moles. N is equal to PV divided by RT. Let's go ahead and do that. Our pressure, 0.957 atmospheres. Our volume, 157 milliliters. I'm going to go ahead and convert that into liters in my head. I just divide that number by 1,000. So I get 0.1570 liters. I've got my gas constant down by now, 0.08206 liter atmospheres per mole Kelvin. And my temperature, which is already converted into Kelvin, 291 Kelvin. Let's double check our units. Atmospheres cancel, as do liters and Kelvin, and we're left over with the number of moles. N is equal to 0.00629 moles of this gas made up of nitrogen and oxygen. Let's move on from there and keep that in mind. Here's my number of moles from the previous slide, the reaction of that copper penny, and now we want to know what's the molar mass. We've seen this formula enough times tonight, that molar mass is equal to mass divided by number of moles. Well, we have the mass of the gas. It's given to us right here. This is our M, and we also have our number of moles that I pasted in from the previous slide. Let's plug that in. 0.289 grams divided by 0.00629 moles. The units of molar mass are grams per mole, and we end up with a molar mass of 45.9 grams per mole as our molar mass. Identify the gas from the previous problem. Well, we calculated a molar mass of 45.9 grams per mole, which is definitely closest to nitrogen dioxide, 46 grams per mole. Very close. Okay, now let's look at another stoichiometry problem that involves gases. TNT, which is trinitrotoluene, an explosive, decomposes according to the reaction shown below. What volume of gas is generated from the explosive decomposition of 5.00 grams of TNT? And we have the molar mass, and this reaction is occurring at standard temperature and pressure. Now, something I want to point out is that it's asking us what volume of gas. It doesn't specify which gas, because we've got three types of gas. We've got nitrogen gas, water vapor, which is a gas, and carbon monoxide gas. That means we've got three types of gases. Well, we're going to need to figure out the number of moles of gas if we want to figure out the volume of the gas. Let me explain why. If we have PV is equal to nRT for all of these gases, and we want to solve for volume, volume is going to be equal to nRT over P. We know R, we know the temperature, it's standard temperature and pressure. My T is 273 Kelvin. My P is equal to 1 atmosphere. We need to figure out the number of moles. From the mass of our TNT, can we figure out the total number of moles of these three gases? The answer is absolutely we can. Let me show you how. If I have 5.00 grams of TNT, and I know that in 1 mole of TNT, I have 227.1 grams of TNT. If I solve this, I would have the number of moles of TNT. What do I know, though, from my balanced equation? I know that for every 2 moles of TNT, can anybody tell me how many moles of gas I form from 2 moles of TNT? Yes, absolutely correct, Bruce. I have 2 moles of TNT. I form 3 plus 5 plus 7. 3 plus 5 plus 7 is equal to 15 moles of gas. And that means all 3 of the gases, the nitrogen gas, the water vapor, which is a gas, and the carbon monoxide gas. And so I put that into my conversion factor, 15 moles of gas. Now, if I work that out, it gives me the total number of moles of gas. When I punch all that into my calculator, I get 0.165 moles of gas. And if you want to put gases, because there's more than one, that's fine too. Now we can plug this number into our rearranged ideal gas equation. The volume, the total volume of all those gases is 0.165 moles multiplied by my gas constant multiplied by my temperature and divided by my pressure. The units of pressure cancel, the units of temperature cancel, and the units of moles cancel, and I'm left over with my volume. And the volume I get is 0.70 liters of gas, or gases, whatever you want to call it. So the final answer is here. Give me a thumbs up if you think you could solve that one. Maybe with a little bit of practice. Good. All right. Right, if we look at this problem, and I do this often with you guys, or at least I try to, you step back and look at the math. There's no calculus here. There's no derivatives, It's just multiplication and division. What's complicated? Interpreting the problem. How do you get used to interpreting these problems? You interpret a lot of them. That means you do a lot of practice. Example 5.11. Calculate the volume of oxygen in liters required for the complete combustion of 7.64 liters of acetylene. measured at standard temperature and pressure? Well, we've got the number of liters of acetylene, and we're going to need to figure out the volume of oxygen that's required to burn up with this 7.64 liters of acetylene. In order to do that, we're going to have to figure out the number of moles of acetylene. But the good news is that we know the volume of our acetylene, we know the temperature is 273 Kelvin, and we know the pressure is 1 atmosphere. From that, we can use the rearranged form of our ideal gas law. PV is equal to nRT. N is equal to PV over RT. And we can solve for the number of moles of acetylene. Once I have the number of moles of acetylene, I can figure out the number of moles of oxygen from a balanced equation. Well, let's ask ourselves, is this equation balanced? You've probably realized by now that it's not. Let's try and balance it. I have 2 carbons over here, but only 1 here. That means I need to put at least a 2 in front of my carbon dioxide. I have 2 hydrogens over here and 2 hydrogens over here. That's balanced. On the product side, I have a total of 5 oxygens. That's 5 oxygens. And I only have 2 here. What times 2 gives me 5? And the answer is 5 over 2. Like that. Now, generally speaking, we don't leave in our balanced equation. There's technically nothing wrong with it. But we're going to take this whole equation and we're going to multiply it by 2 to get 2 acetylene molecules plus 5 oxygens, why they left out the gas, produces 4 moles of carbon dioxide gas plus 2 moles of water. Okay. Now we see the stoichiometric relationship between moles of acetylene and moles of oxygen. Let's solve for the number of moles of acetylene. Number of moles of C2H2. We have our pressure, which is 1 atmosphere. We have our volume, which is 7.64 liters. We have our gas constant. And we have our temperature. Units of temperature cancel, units of volume, and units of pressure cancel, and we're left over with the number of moles of acetylene gas. That number of moles is 0.341 moles of C2H2. Now, I can use my balanced equation to solve for the number of moles of oxygen and thus the volume of oxygen. Let me show you how. I know that I have 0.341 moles of acetylene, and for my balanced equation, I know that for every 2 moles of acetylene that are burned in this combustion reaction, I consume 5 moles of oxygen. Moles of acetylene cancel out, and I'm left over with the number of moles of oxygen. The number of moles of oxygen is 0.853 moles of O2. Now I can take that number of moles of oxygen and I can plug it into the ideal gas equation, PV is equal to nRT, and I can solve for the volume of O2, which is the number of moles of O2 times the gas constant times the temperature divided by the pressure. I have the number of moles of oxygen, 0.8. I'm going to run out of space here, aren't I? Do it here. 0.853 moles times the gas constant, 0.08206 liters atmospheres per mole Kelvin, multiplied by the temperature, 273K. I divide all of that by my pressure, 1 atmosphere. Moles cancel, Kelvin cancels, as do units of pressure. I'm left over with the volume of my oxygen that it would take to combust, completely combust with all of that acetylene, and I get a volume of 19.1 liters. That's the volume of my oxygen, 19.1, 19.1 liters. There is another way to solve this problem. I don't have space to solve it on here, but you can check yourself to see if it'll work, and believe me, it will. And the other option to solve this problem is to use Avogadro's law. Avogadro's law. It says V1 over N1 is equal to V2 over N2. If we solve for V2, which is equal to V1 times N2 over N1, you can just plug in the numbers that you're given. That 7.64 liters of acetylene. I have 2 moles of acetylene in my balanced equation, and I have 5 moles of oxygen in my balanced equation. Go ahead and give it a try. Not now, because I want to move to the next problem, but if you try it, you'll see that that will work too. Either way is perfectly reasonable. Based on my experience teaching this class, most students will opt for the solution that I came up with using the ideal gas equation. Example 5.12, sodium azide is used in some airbags. In automobiles, the impact of a collision triggers the decomposition of sodium azide. This follows, so we end up producing not only sodium metal, but nitrogen gas. The nitrogen gas is made quickly and inflates the bag between the driver and the windshield and the dashboard. What's the volume of nitrogen generated at 80 degrees Celsius and 823 millimeters of mercury by the decomposition of 60 grams of sodium azide? Well, we know the pressure and we know the temperature. We're looking for the volume. If we had the number of moles of nitrogen, we would be able to, we need the number of moles of N2, we could solve for the volume, right? Because PV is equal to nRT, volume is equal to nRT divided by P. Okay, how are we going to get the number of moles of N2? This is just your classic stoichiometry problem. We know that we have 60.0 grams of sodium azide. I've gone ahead and looked up the molar mass of sodium azide, which is 65.01 grams of sodium azide in 1 mole of sodium azide. From our balanced equation, we know that 2 moles of sodium azide produce 3 moles of nitrogen. 2 moles of sodium azide produce 3 moles of N2, like that. Grams of sodium azide cancel, moles of sodium azide cancel, and we're left over with the moles of nitrogen, which are 1.38 moles of N2. This is our volume. Now we can delete that question mark, say that these are equal. Okay, now we've got temperature, pressure, volume, number of moles. Sorry, did I say that is equal to volume? Oh, Mr. Deon, you're losing it. Okay. There we go. Okay, so 1.38, that was equal to, let me just move that over here. Sorry about that. I'm sure nobody's tired of listening to me talk either, right? So there we go. All right, fixed it. Okay, so now we can just plug all of those numbers into our V is equal to nRT over P. 1.3 moles, our gas constant. Temperature, 80 degrees Celsius. I've already gone ahead and converted that into Kelvin. It is 353 Kelvin. And I've also converted the pressure into atmospheres by dividing by 760 millimeters of mercury per atmosphere, and you get 1.08 atmospheres. Atmospheres cancel, moles cancel, Kelvin cancel, and we're left over with units of volume. And we get 37.0 liters. So that's the volume of nitrogen that's produced when we have the decomposition of 60 grams of sodium azide at 80 degrees Celsius and 823 millimeters of mercury. Let's try another one. This one, see if there's enough room to squeeze it all on here. Aqueous lithium hydroxide solution is used to purify air in spacecrafts and submarines because it absorbs CO2. And you can see that's what's happening in this reaction. The lithium hydroxide is reacting with CO2. We end up producing lithium carbonate and water. So basically, it's just a way to consume carbon dioxide that comes out in a spacecraft or a submarine, right? Because it's a closed system and you don't want to pollute the air with too much carbon dioxide. You end up forming water and lithium carbonate, just a solution of lithium carbonate, which doesn't hurt anybody. Well, let's take a look at the question. The pressure of carbon dioxide inside the cabin of a submarine having a volume of 2.4 times 10 to the 5 liters is 7.9 times 10 to the minus 3 atmospheres at 312 Kelvin. A solution of lithium hydroxide of negligible volume is introduced into the cabin. Eventually, the pressure of carbon dioxide falls to 1.2 times 10 to the minus 4 atmospheres. How many grams of lithium carbonate are formed by this process? Well, we can see that we're going to have a change in pressure. And we need to figure out how many grams of lithium carbonate are going to be formed. But in order for us to figure that out, we need to know how much lithium hydroxide is consumed. And so if we write our ideal gas equation, PV is equal to nRT, we can see that T is remaining constant, R is a constant, the volume of the submarine doesn't change, but we're having a change in pressure and we're having a change in the number of moles. So we could write that as change in pressure is going to be equal to the change in the number of moles. Okay? Multiplied by RT divided by V, which I factored out. Okay, I'm kind of going backwards here because it's not what it says in my notes, because we're actually looking for the change in the number of moles. So if you rearrange that formula, you end up with the change in the number of moles is equal to the change in pressure times the volume over RT. That's really what I wanted to get to. Okay, so we can use this change in pressure to decrease, right, from here to here to help us figure out the number of moles of carbon dioxide that's consumed. Let me show you how to do that. The change in the number of moles of CO2 is going to be equal to that change in pressure, which is 7.9 times 10 to the minus 3 atmospheres, minus 1.2 times 10 to the minus 4 atmospheres, multiplied by the volume, which is 2.4 times 10 to the 5, power of 5 liters, divided by the gas constant, 0.08206 liters atmospheres per mole Kelvin, multiplied by the temperature, which is 312 Kelvin. Now, there's a lot to punch into your calculator there, depending on if you have a scientific calculator or a Texas Instruments or whatever, but you end up with the decrease, or the amount of carbon dioxide that gets consumed is 73 moles. That means you used up 73 moles of carbon dioxide, or you consumed 73 moles of carbon dioxide when you introduce that lithium hydroxide into the cabin of the submarine. The question is asking us, how many grams of lithium carbonate are formed in the process? Well, you can see that the ratio of carbon dioxide to lithium carbonate is a 1-to-1 ratio. So if I consume 73 moles of carbon dioxide, that means that I'm going to produce 73 moles of lithium carbonate. Okay, if I've produced 73 moles of lithium carbonate, surely we can determine the mass. Well, 73 moles of lithium carbonate, and I know that in 1 mole of lithium carbonate, I have 73.89, and I've gone ahead and looked this up already, 73.89 grams of lithium carbonate. You can see that moles of lithium carbonate cancel out, and I'm left over with the mass of lithium carbonate, which is equal to 5.4 times 10 to the power of 3 grams. And there is my final answer. And so again, all I did was factor out the gas constant, temperature, and volume from the ideal gas equation. And I said that the change in pressure is going to be related to, or proportional to, the change in the number of moles, or the change in the number of moles of carbon dioxide is equal to the change in pressure multiplied by volume over the gas constant times temperature. 631, let's switch gears again and talk about Dalton's law of partial pressure. So we're going to put the brakes on problems just for 10 seconds here and talk about 2 different gases. Okay, I have 2 different gases here. It's pretty clear they're in 2 different containers. I have a container here with some gray gas molecules. I have another container here with some red gas molecules. And where does pressure come from? Well, if you think about the pressure in this first container, the pressure comes from the collision of those little gray spheres, of those gray molecules, against the walls of the container. And there's a certain number of those molecules. Now, we see that there's a temperature reading. It's down here on our dial. In the second flask, or sealed vessel, whatever you want to call it, okay, we have some red spheres, and there's more of them. So if we have more collisions in our container, it's going to create more pressure, right? Just simply having more collisions overall. And you can see that evidenced by the dial here. It has a higher reading. It doesn't give us a number or any units. This is a qualitative analysis. Now, if we put those 2 gases together in a container, what's the overall pressure going to be? Well, Dalton's law of partial pressure states that the total pressure of a gas mixture is equal to the sum of the pressures exerted by the individual gases. So literally, all you have to do is tally up the pressures of the individual gases, and you get the total pressure. And so this is one of the easiest formulas that you'll ever learn in general chemistry, where total pressure is equal to the pressure of the first gas plus the pressure of the second gas. If there was a third gas, you'd add that, so on and so forth. That formula is shown right here. P total is equal to P1 plus P2 plus P3, so on and so forth. Now remember, this is at constant number of moles in temperature. Constant N in T. And what you really have to understand is that the total pressure depends on the number of gas particles, not whether they're gray spheres or red spheres or blue spheres or helium or argon or nitrogen or carbon dioxide. It just depends on the number of gas particles that you have, the number of moles. Let's take a look at a problem. Exactly 2 moles of neon and 3 moles of argon are placed in a 40-liter container at 25 degrees Celsius. What is the partial pressure of neon? Well, in order for you to understand and solve this problem, we have to cover a different subject. Okay, we have to cover something else, and that is what's called mole fraction. So I'm going to skip ahead, and we'll come back to this problem in a few seconds. Mole fraction is exactly what it sounds like. Is a unit of concentration in which the number of moles of a component is divided by the total number of moles in the mixture. And so mole fraction is the number of moles of one substance, for example, substance A divided by the total number of moles. Let's say you had 3 components in a mixture, A, B, and C. The mole fraction of A would be the number of moles of A divided by the total number of moles of A and B and C. We can rewrite that formula because we know that moles, N, is equal to the number of moles, and we can simplify the formula to this. Mole fraction is equal to the number of moles of A divided by the number of moles of A plus B plus C, or if you want to simplify it even further, you can get the mole fraction of A is equal to the number of moles of A divided by the total number of moles. So that's mole fraction. How does mole fraction relate to pressure? Here's how mole fraction relates to Dalton's law that we just looked at, where Dalton's law was P total is equal to P1 plus P2 plus P3, so on and so forth. The pressure of an individual gas in a mixture is related to the total pressure by the mole fraction. And so if I want to determine the pressure of component 1 or 2 or 3 or 4 or 5 or whatever, I'm going to simply multiply the total gas pressure by the mole fraction of that individual gas. Let's go back to that problem now. My slides are in a little bit of a funny order. Here we go. Okay, what were those formulas? Let's jot them down. We said that P total is equal to P1 plus P2 plus P3. That's Dalton's law of partial pressures. And we also said that P of 1, for example, is equal to the mole fraction of 1 times the total pressure. Now, if you're wondering what's mole fraction is equal to the number of moles over the total number of moles. Now, with these 3 formulas in mind, let's take a look at this problem. I've got 2 moles of neon and 3 moles of argon, and they're in a 40-liter container at 25 degrees Celsius. What is the partial pressure of the neon gas? Well, I know that I have a total of 5.0 moles. 2 plus 3 is 5. That's how many total moles I have. Could I figure out the total pressure? Absolutely, I can. I can solve for P total, which is going to be equal to N total T divided by V. Let's give it a shot. 5.0 moles of both of my gases times the gas constant my volume is 40 liters. I go ahead and I plug that all into my calculator, and I get my total pressure is equal to 1.2 atmospheres. Now that's the pressure of both of these gases. So it's asking us, what is the partial pressure of neon? I'm going to need some room here. And the partial pressure of neon is going to be equal to the mole fraction of neon multiplied by the total pressure. That's going to be equal to the number of moles of neon, right? Because I'm going to solve for my mole fraction. I have 2.0 moles of neon divided by the total number of moles, which is 5.0 moles, multiplied by my total pressure, which is 1.2 atmospheres. You can see that moles cancel out, and I'm left over with just the pressure of my neon. Did I write in the wrong answer for my total pressure? I did. No, it's getting late. Mr. Deon's getting tired. Sorry about that. I already solved the problem and I looked at the wrong pressure. So the total pressure was supposed to be 3.1, okay? That means you'd multiply this by 3.1, and the answer was 1.2 atmospheres. I wanted to get through the problem a little too fast, I think. There we go. And that's the partial pressure of our neon. Again, we see the same thing come up in chemistry class all the time. There's nobody in this class that can't do addition. There's nobody in this class that can't do multiplication and division. What does it boil down to? It boils down to being able to interpret the problem, and the best way to do that is to practice, practice, and then practice some more. Take another look at a problem that deals with Dalton's law of partial pressures. Exactly 2 moles of neon and 3 moles of argon are placed in a 40-liter container at 25 degrees Celsius. Gives us the partial pressure of neon and the partial pressure of argon as 1.2 and 1.8 atmospheres respectively. What's the total pressure? One of the easier problems that you'll see in this class, as long as you know Dalton's law of partial pressures, which is we add up all the individual pressures to get the total pressure. So in this case, our total pressure is going to be equal to the sums of the partial pressure of the neon plus the partial pressure of the argon. 1.2 atmospheres plus 1.8 atmospheres. And we end up with a total pressure of 3.0 atmospheres. Question 5.14. Question 5.14, it says, a mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon. Calculate the partial pressures of the gases if the total pressure is 2.0 atmospheres at a certain pressure. Well, we know our total pressure. Our P total is 2.00 atmospheres. We know the number of moles of neon, the number of moles of argon, and the number of moles of xenon. We also know that the partial pressure of, let's say, neon, for example, based off of this formula, that partial pressure of component 1 is equal to the mole fraction of 1 times the total pressure. So we can calculate the partial pressure of neon as being equal to the mole fraction of neon times the total pressure. What's the mole fraction of neon? Well, if you tally up 4.46, 0.74, and 2.15, you get a total of 7.35 moles. Therefore, the partial pressure of my, or the mole fraction of my neon will be 4.46 moles divided by 7.35 moles. Those units cancel. I'm going to multiply that by 2.00 atmospheres. What do you get? You get 1.21 atmospheres. If we do the same thing with our argon, is equal to 0.74 divided by 7.35. Moles cancel times 2.00 atmospheres, and you end up with 0.20 atmospheres. And if you do the same thing for your, was that for the neon? And I did the argon. And what's the last one? Xenon. Okay. Xenon, we have 2.15. Divided by 7.35. You can see my handwriting's getting a little bit worse here as the evening wears on. Anyhow, multiply that by 2.00 atmospheres, and you end up with 0.59 atmospheres. Now you can do a check in this problem. If you tally up all of these partial pressures, right? If you tally all those up, add together, you should get 2.00 atmospheres, which is the total pressure. And that's what they equal.